Alright, so let's take a look at the June 2011 Section A paper. So, question number 1. Which line A to D shows correctly whether the moment of a force and the momentum are scalar or vector quantities? So, a moment is a force times a distance, so we've got a vector in there, so your moment is going to be a vector. Momentum is most certainly a vector, so that eliminates that one, leaving you with answer D. Okay, so then moving on. The graph shows how the resultant force applied to an object of mass 2.0 kilograms initially at rest varies with time. Okay, so we want to know the speed after 1 second, so we need to add together two areas. So it's 5 times 0.5 and plus 0.5 times 15. So that's 2.5 plus 7.5, which gives you 10 Newton seconds. And if it's 2 kilograms, let's divide that by 2. That's going to give you 5 meters per second. Answer B. Okay, and then question 3. Which of the following is a possible unit for the rate of change of momentum? So momentum has a unit of Newton seconds, so rate of change would be over, which would give you just newtons, because obviously the rate of change of momentum is a force, so that means A is wrong, and it also means B is wrong. So looking at this one, kilogram meters per second is mass times acceleration, which is a force, so it's going to be that one. Okay, for a particle moving in a circle with uniform speed, which one of the following statements is correct? The kinetic energy of a particle is constant. Yep, absolutely correct. The speed is the same and the mass is the same. The kinetic energy is going to be the same because kinetic energy is a scalar, so we're not interested in the direction. A young child of mass 20 kilograms stands at the center of a uniform horizontal platform, which rotates at an angular speed of 3 radians per second. The child begins to walk radially outwards towards the edge of the platform. Maximum frictional force is 200. What is the maximum distance from the center of the platform to which the child could walk without risk of slipping? So essentially what we're looking for is the centripetal force, mv squared over r is equal to 200. That will be on the point of slipping. And obviously we can write that as m omega squared r, which would be more useful here because you've got omega. So we're going to solve for r. It's going to be 200 divided by 20 times by 9. So 20 times by 180, so 200 over 180. So there's a factor of 20 in all of those, so 10 over 9, which is going to be 1.1, I think, but let's just double check by calculating it. And it is 1.1, which is the first answer, answer A. The particle travels at a constant speed around a circle of radius r with centripetal acceleration A. What is the time taken for 10 complete oscillations? So, the angular acceleration is equal to omega squared r, which means omega squared is equal to a over r. 10 time periods will be equal to 10 sets of 2 pi over omega, which will be 10 2 pi over square root of a over r, which will essentially be 20 pi square root of r over a, which is, if I'm not mistaken, answer D down here. Okay, so the frequency of a body moving with simple harmonic motion is doubled. If the amplitude remains the same, which one of the following is also doubled? Well, so double the frequency, you'll halve the time period, so that's certainly not going to change. The energy is related to the amplitude, which stays the same, so that's not going to be doubled. So we're down to the maximum velocity and the maximum acceleration. So Vmax is given by 2 pi fa. So if you double frequency, you're keeping A the same, Vmax would double, so that one works. Let's just make sure A max doesn't work. That's going to be 2 pi f squared A. So if you double f, you'd actually times by 4, so it's not that one. So it gives you answer C. The maximum velocity will be doubled. So move on to the next question. The time period of a pendulum on Earth is 1.0 seconds. What would be the period of the pendulum the same length on a planet with half the density, but twice the radius of... So, if you double the radius, that should, in theory, mean that the density would be divided by 8, because it's 2 cubes, so the density, according to just the radius, should be divided by 8. But we know it's only halved, so that means the mass must have been multiplied by 4. So r squared would have also been multiplied by 4 because r has been doubled. So the m and the r are going to cancel out, meaning that the field strength on this planet is g. So we've changed nothing, so the time period is going to be exactly the same. This one is a tricky little question, so I'll just quickly recap. So, if you double the radius, you essentially should mean that the volume has been multiplied by 8. So, with the same mass, the density would be 1/8 of what it was before. But it's only half, so you know that the mass must have counted that. So the mass must be 4 times, so that you end up with 4 divided by 8 gives you half the density. So g, the calculation, has m on the top line, so that top line has been multiplied by 4. It has r squared on the bottom line, so it's 2r squared, so times by 4, and those cancel each other out, meaning the field strength on this planet is also g. Which one of the following statements always applies to a damping force acting on a vibrating system? So it is always in the same direction as the acceleration. It certainly is not. It is in the same direction as displacement. Again, very often, not usually. It acts in both directions. It is in the opposite direction of velocity. That is absolutely true. Damping acts against velocity at all times. And then its proportional displacement, no, it's affected by the velocity. So it's answer C for this one. Masses of m and 2m exert force F on each other when the distance between the centres is r. What is the force between masses of 2m and 4m when the distance between the centres is 4r? So what we've got is we've gone from a top line of a force equation of 2m to 8m when we multiply the forces. It's going to be m squared, isn't it? M squared like this. So essentially this should result in you having 4 times the force. We've gone from a bottom line of being r squared to 16r squared once we've gone through, which should give us 1/16 of the force. So putting these two together, we should end up with 1/4 of the force, so option number A. So a planet has a radius half that of the Earth's radius and a mass 1/4 of the Earth's mass. What is the approximate gravitational field strength on the surface of the planet? So if on the top line we've got a 1/4, and on the bottom line essentially what we've got is a half squared, which ends up being 1/4 over 1/4, which is just 1. So it should have a field strength around the same as the Earth, which is approximately 10 newtons per kilogram. Also, we know it's 9.8, but it's approximately. The surface of the Earth, the gravitational field strength is g, and the potential is v. The radius of the Earth is r. an object whose weight on the surface Earth is W is moved to height 3r above the surface. So it's a total distance of 4r from the centre of mass of the Earth when it was previously r. So it's gone from being r to 4r. Which line gives the weight of the object and the gravitational? So the weight force is proportional to the distance squared. So the distance will be multiplied by 4. So the force will be 1/16 of what it was before. So we can eliminate those ones that say a quarter. Potential only varies linearly, so potential will be a quarter of what it was before. So it's going to give you answer A. A satellite of mass m travels in a circular orbit of radius r around a planet of mass m. Which one of the following expressions gives the angular speed of the satellite? So, we're using the angular speed, so we're going to end up essentially with this expression. Equated like this, so as usual we can cancel the m's. So what we want to do is take r to the side and square root. So when we take r across the other side, we ended up with r cubed, and we end up square rooting. So we get answer D. An electron and a proton are 1 times 10 to the minus 10 meters apart. In the absence of any other charges, what is the electric potential energy of the electron? So that's QQ over 4 pi E0R. So the charges of the two are both 1.6 times 10 to the minus 19. But obviously the charge is negative, so it's squared by 4 times pi times by 8.85 times 10 to the minus 12 times by 1.0 times 10 to the minus 10. And calculate, and we get a value of minus 2.3 times 10 to the minus 18. You would expect it to be minus because what we've got in here is the charge of a proton and charge of an electron, so a positive number times a negative number, so we end up with a negative number. Okay, an ion carrying a charge of 4.8 times 10 to the minus 19 travels horizontally at a speed of 8 times 10 to the 5 meters per second. It has a uniform vertical electric field of field strength 4,200 volts per meter, which is directed downwards and acts over a horizontal distance of 0.16. Which of the following statements is not correct? So let's label this diagram a bit. We have a series of positive charges up here because field lines go from positive to negative. So what's going to happen is it's going to be deflected in this direction by the force. Okay, so if it's travelling at 8 times 10 to the 5 over a distance of 0.6, so distance over, distance divided by velocity should give you the time it takes. 8 times 10 to the power 5, which gives you 2 times 10 to the minus 7. So statement A is absolutely correct once you do distance divided by speed. The force on the ion acts vertically downwards at all points. It does, because it goes from positive to negative, so that statement there is absolutely correct too. The magnitude of the force exerted by the field is 1.6 times 10 to the minus 19. So we've got a field strength of 4,200, so we times it by the charge, 4.8 times 10 to the minus 19, 2.0 times 10 to the minus 15, so that is wrong when we do that. And the horizontal component of the velocity is unaffected. It is because the force acts perpendicularly, so that's correct. So C is the one that is incorrect. The electrostatic potential at a distance r from a positive point charge is 45 volts. Potential increases to 50 when the distance from the charge decreases by 1.5 meters. What is the value of r? So let's think about how we calculate potential. So the 45 is equal to Q over constant times r. and 50 is equal to the same charge divided by the same constant, but times by r minus 1.5. Okay, so to go from 45 to 50, over times by 10 over 9. So 10 over 9 times by q over kr is equal to q over k r minus 1.5. So we can cancel the q's, we can cancel the k's. So we end up with 10 r minus 1.5 is equal to 9r. So we're going to end up with, when we rearrange those, 1r is equal to 10 times 1.5, which is going to be 15 meters, which is answer D. Okay, a 400 microfarad capacitor is charged so that the voltage across its plates rises at a constant rate from 0 to 4.0 volts in 20 seconds. What current is being used to charge the capacitor? So we need to work out what the final charge is, and then we can divide by the time. So Q would be CV, which is going to be 400 times 10 to the minus 6 times 4.0, which is 400 times 10 minus 6 times 4, which is 1.6 times 10 to the minus 3. So that's your charge divided by time should give you the current, which is 8 times 10 to the minus 5, or 80 times 10 to the minus 6. So answer D there. A capacitor, a capacitance C, stores an amount of energy E when the potential across it is V. Which line A to D gives the correct storage energy when the PD, and PD when the charge is increased by 50%? So for a fixed capacitance, if you increase Q, you also increase. So we've got 1.5 Q, and we'd also therefore have 1.5 V, because they're directly proportional to each other for a fixed capacitor. So the energy would be 1.5 squared, which gives you 2.25. So we can eliminate the first two because they don't give the correct energy. And the potential difference would be this one. So it's going to be answer number C. Capacitor capacitance C discharges the resistor of resistance R. Which one of the statements is not true? Time constant will decrease if C is increased. So remember, time constant is RC. So if R is the same, but C is increased, the time constant will increase. So actually the first statement is the one that's wrong, so that's the answer to this question. Graph shows how a charge on a capacitor varies with time as it is discharged through a resistor. So what I want to know is the time constant of the circuit. So it's the time to get to 37% of its initial value. So 0.1 times 0.37 is 0.037, which is around here. So we're looking about 5 seconds to get to essentially 37% of its initial value. So that's answer C. Two charged particles P and Q move in circular orbits in a magnetic field of uniform flux density. The particles have the same charge, but the mass of P is less than the mass of Q. T is the time taken for the particle to complete one orbit. Time Q is the time for Q to complete one orbit. Which of the following is correct? So if we think about it in a magnetic field, we're going to do BQV is equal to m omega squared r. So we can put that 2 pi over t, which is omega, or squared, is going to be BQV V over mR. Okay, so what we've got, the mass of P is less than the mass, so that would make the 1 over the time period P if the mass of P is less. So we're going to have a smaller number on the line, so there's going to be a bigger. So therefore the time period of P is going to be smaller than the time period of Q, based on that equation there. So as mass gets bigger, 1 over T, so mass gets smaller, 1 over T gets bigger, so T gets smaller. So essentially you end up with this one, which is answer C. Graph shows how flux linkage in phi, I think it is, through a coil changes when the coil is moved in a magnetic field. The EMF is the rate of change of this, so the gradient. So initially your EMF is going to be the same but constant, and then becomes 0 after T0, which is answer B. A bar magnet is pushed into a coil connected to a sensitive ammeter as shown in the diagram until it comes to rest inside the coil. Why does the ammeter briefly show a non-zero reading? So the reason there's a non-zero reading is because an EMF is induced, which then causes a current to flow in your circuit. So there must be a change in the flux linkage, and then essentially the flux linkage must become constant, so there's no change, which is why there's a briefly. So we're going to have a change, then becoming constant. And so if we're looking at, we want something that has become constant, so it's not going to be either A or C. And then, so which of B and D is it going to be? Well, if it's going to give a value, you're not going to decrease the flux linkage, so you must have increased it to give you a value. Okay, 24. The above graph shows how the EMF varies with time for a coil rotating at angular speed omega in a flux density B. Which one of the following graph shows how EMF varies with T for the same coil is rotated at angular speed 2 omega uniform magnetic field of flux density 0.5 B. So what we're going to get is double the frequency if you have double the angular speed, so we'd expect twice as many cycles. So if there's one cycle in 20 seconds, there should be one cycle in 10 seconds, which is not A, it's not C, but it is both B and D. And you'd expect the EMF would remain the same because the rate of change of flux linkage is the same because you've halved B but doubled the speed. So you'd expect exactly the same EMF to appear, which is answer B. Final question. Which one of the following is not a cause of energy loss in a transformer? Let's start from D. Resistances definitely do. Reverse magnetism, that does as well, so that's not the answer. Reduced currents definitely do. So insulation actually is a way to mitigate one of them, so it is definitely not a cause of energy loss. It's something to help you with that.